Okay, before the break, guys, we before the break, we stopped talking about bond energies. So before we get into bond energies and start having questions and examples about like how to calculate the uh, enthalpy of a chemical reaction using bond energies, we need to watch a little video about this. Just quick video, okay?
All the periodic peaks for those that contain membrane. Mitochondria are double membrane.
Sorry, this is biology. No problem. Okay.
So we can't see the screen.
Yes, I will share my screen with you. Just give me a second. Okay, share my screen. Oh, before I have to share the sound as well. Yeah. Okay. Tell me that you can see my screen and
We're going
you
to take a
can
look at
hear the
bond
sound as
energies
well.
and
Yes,
see how we can use
see
them
it
to
Okay.
determine
and
what.
hear.
Perfect. So let's watch this video, like 4-minute video, and we'll discuss this after that.
In today's video, we're going to take a look at bond energies and see how we can use them to determine whether a reaction will be exothermic or endothermic. When we say bond energy, what we're actually referring to is the amount of energy needed to break 1 mole of a particular covalent bond. So if I had an atom of hydrogen bonded to an atom of chlorine and said that the bond energy was positive 431 kilojoules per mole, that means we'd have to supply 431 kilojoules of energy to break 1 mole of these bonds. And remember, 1 mole would be 6.02 times 10 to the 23 bonds, which is Avogadro's constant.
Question: who can tell me if, okay, he said if you want to break the bond HCl, you need 431 kilojoule per mole, and it is positive to indicate that it is what? Needed, right? Absorbed. Yes, exothermic and endothermic, right? So this is considered as endothermic process. Yes? David, Royal, yes?
Yes, sir.
Yes.
Perfect. So the breaking a bond needs energy, and this is like it makes sense in our daily lives. If you want to break any like a stick, for example, you need to pay some energy, right? So to break a bond, you need energy, and in this case, HCl, as an example, needs 431 kilojoule per mole, which means Avogadro's number of this HCl bond. If you have 6.02 times 10 to the power of 23 HCl bonds, okay, you need 431 kilojoule to break all these bonds. Okay, you can find per one bond by dividing this amount of energy by Avogadro's number, right? Then you can get amount of energy needed for one bond. Okay, this is not my question. My question is, who can expect the amount of energy that will be produced if we form the HCl bond? Any idea?
So, so wouldn't it be equal to the energy out?
Exactly, exactly right. It will be the same exact value, but the only difference will be what? The only
The
difference will be
direction,
what? Which is
the positive or negative.
excellent, excellent, right. So it should be in this case 431 kilojoule per mole, but negative, which means heat released by the formation of HCl bond. Okay, so always, guys, when we say if you pay energy to do something, when that thing, if you reverse the process, the same process that you paid energy for will provide you with the same amount of energy. It will be pay you back the same amount of energy that you already like gave to it, right? So it's the same amount of energy, but one of them will be absorbed. The other direction of the process will be produced, right? So gained and produced. Yes. So the same amount of energy. Okay, back to the point. So breaking this bond HCl needs amount of energy. Let's continue.
So breaking bonds is actually an endothermic process because it requires energy from the surroundings. On the other hand, bond formation is exothermic.
Yes.
So if we were to form 1 mole of hydrogen chloride bonds, it would release 431 kilojoules of energy to the surroundings. So if we took a simple reaction, like hydrogen plus chlorine goes to form 2 hydrogen chloride, and we were to think about it in terms of molecules, then we can see that for the reaction to work, we'd have to break this hydrogen-hydrogen bond and this chlorine-chlorine bond, which would both require energy and be endothermic process.
That means always, guys, to start a reaction, we need energy. We need to provide the reaction with energy, right? That's what we always call it, what? Yes, activation energy, exactly, the activation energy. So any chemical reaction to start, it needs energy, okay, to start breaking the bonds, all right? So it needs what is called activation energy. So breaking these bonds in blue, they need energy. So the reactant side need energy. So this part of the equation or the calculation process, okay, is endothermic, okay, right? So energy is absorbed or used. On the other side,
and then would form 2 of these hydrogen-chlorine bonds, which would release energy and so be exothermic processes. To determine if the overall reaction is exothermic or endothermic, though, we'd have to compare the total amount of energy required to break these bonds to the total amount of energy released when these bonds form.
right?
In an exam,
In this
you'll normally be
case,
given a list or a table with all of the bond energy values that you'll need. And to work out the overall energy change, we just do the energy required to break bonds minus the energy.
yeah. I'm gonna give you like when we start having examples, I'm gonna give you like a very like straightforward way how to calculate the delta H R for the reaction using bond energies. I will show you what exactly you need to do. Okay, so for now, just understand the whole idea, and then we will go over a couple of questions or examples.
Released by forming bonds, which in our case would be 436
So
for
energy
the
required
hydrogen
minus
hydrogen
energy
bond,
released.
plus 242 for the chlorine-chlorine bond,
Right. This is always
minus 2 times 431 for the bonds within the 2 hydrogen chloride molecules.
who can tell me why 2 times 431? Why this number 2? 2 bonds, HCl, right? Yeah. So that's why this is what I'm gonna tell you actually when you start having examples shortly. You should for yourself, like so that you don't miss any bond. Try to draw all the bonds you have, okay, so that you don't miss or you don't like ignore any of them, okay, accidentally. So I will, okay, we will have examples and I'll explain exactly what you need to do.
Which simplifies to 678 minus 862, or negative 184 kilojoules per mole. And
So always the bond broken, the energy needed for or to break bonds minus energy produced while the bonds formed, okay, or forming in the product side. So always energy required minus energy produced, okay. Now if the product, the final answer is negative, that means the overall reaction, the overall process, or the overall chemical process is an exothermic process. If this value of energy, the net value of energy is positive, that means the overall chemical reaction is endothermic. Make sense, guys? Does this make sense? Yes? David Royal, does this make sense to you?
So to calculate the overall energy, we go in energy to break bonds minus energy released.
Yes, always like this.
Okay.
Okay, so when you get negative sign, that means the overall reaction is exothermic. When you get positive sign, that means the overall reaction is endothermic. Okay, so it's like if you want to start a business, for example, you need what?
Capital.
Amount of money, right, to start the business, right? Yes, you have to pay first. You can't you can't start a business with no money. No way, right? You have to pay first. Okay. And when the business starts, okay, and start running, okay. So at the end, you will calculate the amount of money you get, okay, compared to what you already paid. You say, oh, that business is like I can get profit from this from this business, right? Or I'm losing, actually. I'm losing money, so I have to close it, right? You can tell by comparing what you get with what you already paid, okay? The capital that you already paid. Yes? So this is how we deal with bond energies.
If you get a negative value like this, it means the reaction must be exothermic, as the chemicals are losing 184 kilojoules of energy to their surroundings.
Why it's per mole? Why negative 184 kilojoule per mole? Because all these values that we use, 436, 242, 431, are what? Yes, kilojoule per mole. So everything will be kilojoule per mole, okay? Yes.
Before we finish, let's try one more example. Nitrogen and hydrogen react together in the following reaction. Calculate the overall energy change for this reaction. Now, although you don't have to, I think it's definitely easier if the first thing you do is...
Before he continues, tell me any, like something, any idea, anything you get from the table. Think about any idea you can conclude from the table. Look at the bonds and the values, compare, see. Who can? This question is for smart people, so who who thinks he or she is not smart, so just relax, okay? No, I'm just kidding. Yeah, so yes, try, guys, try.
Hydrogen bonding, the NH bonding has the lowest amount of energy despite being the strongest intermolecular force.
Hydrogen bonding, David, is intermolecular forces, which means like we're talking about not chemical, physical change, like from solid to gas or to liquid or liquid to gas. This is like, but we're talking about just bonds now, like covalent bonds. Compare between, yeah, what is it? Yeah, yes, for sure. Yeah, I mean, now just compare between these bonds in the table. Yeah, that's good. Good start. Triple bond. Yeah, what about triple bond?
Oh, so I see. There is
Yeah,
two pi bonds and one sigma bond. So that means
okay.
more energy is required to break two pi bonds and one sigma bonds than that of one
Right.
sigma bond. Yeah.
Exactly. So as you see, triple bond here, as you know, triple bond is one sigma and two pi bonds, right? So in this case, you are breaking three bonds, regardless. Okay, there are three bonds, right? Yes, three bonds compared to single. Look at the values. obviously the triple bond needs more energy. It's exactly like if you are holding, like in your hands, you're holding one pen and you want to break it. Okay, don't do that for fun, please. Okay, if you want to break it, or a pencil, for example, uh, it's easily, right? But if you have a three, you need what? Obviously, much. Don't say much. We're not going to say more energy, right? Yes, more energy. To break three pencils, you need more energy, more than what? One pencil, right? If it's two pencils, in between, right? Yes, between single and triple, right? One pencil and three pencils, right? So obviously, when it's triple bond, you should expect the energy needed to break triple bond will be higher than single and double, right? Excellent. Thank you, guys.
Draw out all the molecules using their displayed formula so that you can actually see the bonds.
Is the 3D structure for ammonia in this case right? In this case, regardless, we're gonna deal with three bonds, three NH bonds, no problem. But I mean, the 3D structure, is it right? Ammonia? It should be what? Trigonal? Right, trigonal pyramid. Yeah, right, Hannah, thank you. So because there is a lone pair on the nitrogen, so it will be a trigonal pyramid. But why I'm asking this? I'm asking this because it doesn't matter like what the 3D structure is, because we care about what types of bonds we have. That's it. So in this case, we have three NH single bonds, right? Times two molecules, so total is six NH single bond. David and Royal, I want you to make sure that you get this point.
Understood, sir.
Yes.
Yeah.
Okay, perfect. Royal,
I'm not sure, sir.
you're not sure. NH3 here in this picture here, in this example, the way he drew the NH3 3D structure is not right. It should be what? Trigonal pyramid, as Hannah said. It should be trigonal pyramid because there is a lone pair on the nitrogen. Okay, so when you draw Lewis structure, you find it as NH3. Okay, I don't want to. In NH3, it's like NH to the right, H down, H left, for example, and a lone pair on top, okay, of the nitrogen. So the 3D structure will be what? Trigonal. Sorry, it'll be yeah, trigonal pyramid, okay. But what I'm trying to say is we don't care about the 3D structure in this case. What we care about is what type of bonds we have and how many of them. Like in this case, we have NH, 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 okay? Regardless if it's tetrahedral, sorry, trigonal pyramid, planar triangle, we don't care. We care about we have three NH bonds and we have two molecules, so the total is six NH bonds, okay? This is what we care about. Yes? Ryan, yes?
Yes, sir. Thank you, sir.
No problem.
On the left, we can see that we'll need to break one nitrogen-nitrogen triple bond and three hydrogen-hydrogen bonds. While on the right, we'll have to form six nitrogen-hydrogen bonds. So if we recall our equation, which stated that the overall energy change equals the energy required to break bonds minus the energy released by forming bonds, we can just plug in our numbers. So 1 times 941 plus 3 times 436, which we can put in one big bracket, minus 6 times 391, which simplifies to 2,330 minus 2,346, giving us minus 16 kilojoules per mole, which makes it an exothermic reaction.
Okay.
Anyway, that's all for today. So if you enjoyed it, then give us a like and subscribe.
And question, guys, about this video, what you watched in this video. Any question, any point you didn't get, You want to ask about? Please ask, please. Please ask. No? No questions? Okay.
No question, sir.
Okay, no problem. Okay, this table, guys. Now let's go into like having more examples. Bond energies. Maybe you ask yourself like, okay, from where can we get these values, like the triple bond in it's 900 something. From where? There is a table. These values, please do not memorize them, okay? Yeah, this table will be given as I told you at the beginning, if you remember, there is a data booklet at the end of the semester. I will give it to you. It's on Canvas anyways. I'll give it to you during the final exam. That has all the formulas you need, all the values you need, all the tables you need, okay? So you don't need to memorize any of these things, okay? Back to the point. Now, this table shows average bond energies, kilojoule per mole. So any value, as you see, take this as an example. Oh, sorry. Any value, take for example this. In single bond O, 201 kilojoule per mole. If this amount of energy, if this bond is being formed, it produces this amount of energy, right? If we need to break this bond, we need this amount of energy, right? As we said at the beginning, forming produces energy, exothermic process. Breaking bond, endothermic process, right? Okay, so these values given as you see, given in the table, you can just use them whenever you need them and whatever you need from this table. There is a little point you need to pay attention to, which is this part. Look at, where's the star here? Do you see it? C double bond O. C double bond O, you can find it, if you still remember from organic chemistry, you can find it in all carbonyl compounds, which are what? Could be carboxylic acid, right? Could be aldehyde, that's right. What else, guys?
Could be
Ester.
ester
Yes.
or no.
Ketone.
Ketone, yeah.
Yeah. Yes. Could be amide. Yeah. So any of these molecules could have C double bond O. So if you have for example, aldehyde, okay, in the reaction, you have aldehyde. So you will have C double bond O. Yeah, you'll have a bond which is C double bond O, right? So you will get the value from the table as C double bond O here, as you see. You will get this value, 745. But if you have CO2 from a combustion reaction, and you know, all combustion reactions have CO2 as a product, okay? Almost. I mean, as I said, with some exceptions. Okay, CO2 is or has C double bond O and C double bond O. So it has C double bond O. In this case, you don't use 7450. Sorry, 745. You don't use this value in this case. In the CO2 specifically, you use 799. Okay? Please keep this in mind. When the reaction has CO2 and you have this bond, C double bond O, from CO2, you should use 799. If C double bond O, any other compound that has C double bond O, you can use 745. Okay? Yes, this is very important point. Many students actually make mistake in this point. Okay, be careful. As you see in triple bond 941, in double bond 418, in single bond somewhere here 160. Can you compare between them? Look at this. In single bond 160, in double bond 418, almost 4 times, right? In triple bond 900, almost 9 times the single bond, right? Don't think that it is, since it's double, it should be double energy of single bond. No, because sigma and pi is different than sigma. So they are not two sigma, okay? So each one will be the same value. So don't worry. I mean, don't be fooled by this point, okay? Okay, example, and no. Let's take a quick example. H2 plus F2 produces 2HF, and the question asks for what? For delta H reaction, delta H reaction. We will have Kahoot if okay, if you want to just quickly. And delta now we need to find delta H reaction. Okay, the enthalpy change of the reaction H2 plus F2 produces 2HF. Now what to do? H2 plus F2 produces 2HF. As I said earlier, I will tell you what to do exactly step by step. Now, I will make a line here, okay? And I'll find all the energies here for the reactants minus all the energies for the products and equal, this is the value of the overall delta H naught reaction, okay, will be here. Now, let's find it. Before that, just before doing that, we need to draw Lewis structure. And to be honest, this is the most annoying like part or step in this kind of reactions, just to draw Lewis structure. But since we already studied this topic, how to draw Lewis structure, it should be easy, right, to do it now. Now H2, how to draw Lewis structure for H2? It will be like this only, right? What's the ultimate goal? To show all the bonds, right? This is the point. Now H2 is HH, I2, sorry, F2 is FF single bond. This is what you will find, and HF will be just single bond HF and single bond HF. And as I said, I would show if there are two HF, I would draw two HF. Okay. I mean, what I'm trying to say is, don't write like this, guys. It's up to you. If you don't miss any of them, it's okay. You can write 2HF like this, okay? Look at the board, please. 2HF. You can write it this way. It's okay. Otherwise, what I prefer is to keep the two molecules this way, okay? Now, HH bond is what? It's given in the question here to just to make it quick. HH DHH equals 432 kilojoule per mole. Do you see this value? FF, tell me.
So are the bond energies always given?
Yes, given in the question. Yes, always. As I said in the final or the unit test very soon, I will give you the table so you can get the value you want. But in the final exam, I will give you a data booklet so you can get any value, any formula you need from that booklet. Okay. The booklet is on Canvas. I told you at the beginning of the course there is a booklet on Canvas. Okay. Now, if single bond, what's the energy? 154. Excellent. So this will be added together minus, as I said, and HF. What's the value of HF bond? 565 times 2. Okay, equals what? And this is the kilojoule per mole. This is the final answer. Now tell me. The overall or what? No, 432 plus 154 equals
544.
Yeah, so this is 5,
Oh
8,
no.
6,
I meant together 544.
5, 6, 5 times 2, 1, 1, 3, 0. So negative 1130 plus 586 equals negative 5. You said 544, right?
Yes.
Yeah. So so this is what delta H reaction note. Okay. Delta H reaction. Regardless, you can write it. Delta H reaction. Okay. Negative 544 kilojoule per mole. Yes, guys. Yes.
Yes,
So,
sir.
Okay, perfect. So I'm
so
gonna stop at this. Yeah, a question.
I wanted to ask, is there a reason as to why the hydrogen bonding has a higher energy than the FF, even when they both have single bonds?
Yes, it has. Yeah, for sure, it has an explanation. The H bond, since the hydrogen atom is small, okay, so the electrons, the shared pair of electrons between the H and H will be closer to both nuclei. So the relation or the attraction between the nucleus and the shared electron will be stronger than in case of fluorine, because fluorine atom is larger in size. So the shared electrons are away from both nuclei. So the attraction between the shared pair of electrons and the nucleus will be weaker than the hydrogen case. Okay.
Thank you. Yes.
Okay. Now let's stop at this point, like doing examples. We will continue tomorrow. Tomorrow we'll review this topic by taking or having more examples. Now let's play some. Let's have fun with Kahoot game. Okay. By the way, I added already the marks that you got last time for the Kahoot. Okay, I added them to the midterm exam. Okay. Ready, guys?
So what's the
Ready?
code? We don't have the code. Okay.
Yeah, you'll see it now. You have it now? Do you see my screen?
Yes.
Okay, good. Quickly, guys, because we have only 10 minutes. You have 20 questions. Royal, Hannah, David. Where's David? Quickly, David. Ah, that guy. That guy. Who's that guy?
No,
David,
sir,
if
it's
you,
me. It's me. I'm
I
that
know
guy.
it, I know it's you. But if you get the first place, or I'm not gonna give you any mark. Why? Because I'm gonna give marks to David, and David is not in the competition here.
Oh, wait, sir,
No,
sir,
no, just
sir.
kidding. Just kidding. Go ahead. Okay. Types of reactions and chemical energy. What are substances called that get used up in chemical reaction? Used up. Good. Excellent, guys. So rail is the fastest. Okay, so far. Formed during chemical reactions. Yeah, excellent. Let's see. Oh, Royal. Not David. I said David. No, Royal. Sorry. Oh, what is the scientific name for reaction where fuel is burnt? What do you call this? Excellent. Oh, the competition is high. The competition is combusting. It's burning. Excellent. Who answered? You? No.
Oh my days. That's me.
Ryan. No. Okay. What's the correct word equation for the combustion of methane? You who answered carbon dioxide, there should be water here.
Sir, I make mistakes.
No
And mistakes should not
problem.
be made again.
I know, because sometimes you rush the thing. It's okay. Good. Excellent. And renewable. What is a compound? Here mixed. This is wrong. It's not mixed. Bonded together.
Oh, sir, I just keep on making mistakes.
No, take it easy, okay? Don't rush. No rush. Excellent. Decomposition.
I should slow down. Yo,
Thermal decomposition. Thermal decomposition. Okay. Metal cabinets decompose and produce gas that turns metal. I know this is like old stuff. Yeah, you studied this before, but why not to review? Right. Same. Conservation of mass. It should be both on both sides the same mass. Reactants and products. Excellent, yes.
is it only 3 guys that are playing this game?
Yes. I have 3 absent students today out of 6. Muhammad is doing test, as you know. Stephanie, I don't know why she's not here. Fessler, I think he's sick. What happens to the temperature during in the thermic reaction?
Yeah,
Don't
because
rush.
yo, it's too competitive.
What's that?
It's too competitive, sir. Hannah is still in the top place, and oh my days, there's no way. I thought it increases. Jeez.
I know, I know. That guy is going up. Okay, yeah. We just discussed like something similar to this. Yes. Absorbing heat through the path. And oh, why, guys?
Oh my days.
Exothermic
Oh
reaction.
my days.
Yeah, we just explained this. Exothermic
I
reaction
know.
because through the path, it is being the heat is being given off, right? Or out. So that's why the end point becomes lower in energy than the starting point. Yeah. Right. To break bonds. To make new bonds, this is not the point why reactions take some energy. To break the bonds. Yeah. Right. Good. Second last question, guys. All right. Last question. All right. Speed up reaction doesn't get used. Yes. If it's used, or if we use even part of it, it will be part of what? Reactants. Yes, it will be one reactant, one of the reactants. Excellent, guys. Thank you so much. And let's see who's.
It's me. Oh my days. Oh my days. Oh my
Yeah,
days.
bro.
And
I
there's
started
no
from
way.
the bottom,
That
now I made it to
guy.
the top. I'm that
That
guy
guy.
for a reason.
You
what they call
you
me.
are amazing. That guy. Yes. Yeah, but again, as I said, I don't have that guy in my list, so I can't.
No, sir, please, you know who it is. You know who it is.
All right, thank you so much, guys. Thank you, and yeah, I'll see you tomorrow, and we'll have more examples, and continue to have the finding delta H reaction, the enthalpy of a reaction using energy of formation. Okay. All right. Enjoy
Thank you, sir.
the rest of your
Awesome.
day, and see you tomorrow. Take care.